Great, thank you very much. Thank you very much also to the organisers for inviting me today. It's a privilege to be talking again at ECT Star. It's a shame that we're not all in the same room in Trento. It would have been nice to meet you all. So I was given the title to talk about charge radii measurements in the heavy region. So there's kind of quite a large region of nuclei to talk about. So the overview of the talk, I sort of focused on the sort of background nuclear physics that perhaps charge radii measurements contribute to understanding, and the role that isotope shift and charge radii measurements have as tests for internucleon interactions and many-body methods. I'll also talk a little bit about nuclear isomers and their role, and perhaps what they can offer as a way of isolating some of the effects and removing some of the systematic errors associated with charge radii measurements as well. And then focus on the shell closures at n equals 82, n equals 50, and also the new shell closures at n equals 32. And then with some concluding remarks. So most of this talk really leads with open questions, and I think the end of the talk will just provide open questions to the community. I'm not sure I will have any of the answers to those questions, but I think that was the purpose of this talk, is to really identify where we are. So I know there's quite a diverse community here, and so I mean probably most of you are aware of the emergence. I mean when I present this to students at undergraduate level, is I do have to remind myself just how impressive it is that we have this collection of 100 to 200 nucleons in a box. And yet this rather complex system has regular structure that emerges out of it. And we see those as the shell closures, and we see them in many different observables. So here I show mass and I show the 2+ energies, and we see this regular structure emerging at shell closures at n equals 50, 82, 126, and we see the same patterns happening in the E2 plus energies. And we expect, in particular for double shell closures, where we have a double magic number, so for nickel 78, for tin 132, that we would observe the evidence for this being a shell closure in all of the observables, in shape, and binding energy, and excitation energy, nuclear moments, and in half-lives. And these are just, again, some of those examples of how we observe those. And the question marks happen associated with structure that emerges in the mid-shell, such as the n equals 40 mid-shell effects and elsewhere. And these effects are observed in one observable, such as the E2 energies, but not then in other observables, such as mass or in the charge radii. And so that really then lends questions to what is really happening. Do we understand it? Now, in the last few years, there's been new shell closures emerging at n equals 16 and n equals 32 and 34. And then what this, in my mind, highlights is that we yet don't have a proper or a full understanding of the interplay between the tensor interaction and central forces component of the NN interaction, and that's not fully described. We also see evidence, and this was highlighted also in Wilfred's talk yesterday, weakening of shell closures as we move along either isotope chains or isotone chains. And we know that the NN interaction alone doesn't reproduce shell closures above N and Z equals 20, and these require 3-body forces and higher order forces. And so this is articulated quite well with the new shell closures at Oction 24, in this example on the right, which requires 3-body forces to really describe the observed masses. So we can then look at these recent results, and I mean, there's been a huge amount of work studying these isotopes and using the latest interactions to really understand what's happening. And we saw these shell closures arising from measurements, from observations from neutron removal and knockout reactions in calcium and oxygen. And then the subsequent shell model, well, subsequent nuclear theory calculations, which introduce higher order forces, so really such as the three-body forces and the next to leading order interactions, describe these new shell closures, and also give us information about then the limits of nuclear existence, predicting then that calcium-60 is the last bound isotope. So that's sort of just setting the stage. So where does charge radii step into this, and why have I introduced it with a lot of mass measurements and knockout reaction information? Well, we also know that nuclear theory struggles, or let's say it is a challenge for nuclear theory to reproduce simultaneously charge radii measurements and masses and the energy of the system. And this is highlighted nicely in this plot by Goethe. And here we see that, you know, the comparison where we walk along the double shell closed nuclei, where we get good agreement across all theories in mass and in energy. But when we come to reproduce the charge radii, the majority of theories break down, and this remains a challenge. And of course, as we go to heavier systems, this challenge only grows. So we've already seen, you know, how optical measurements can provide a model, let's say a model independent, or a view of the nucleus which is independent of any, or doesn't introduce any assumptions associated with a particular model, is perhaps a better way of saying it, of the nucleus, extracting the charge radius. Now, focusing on charge radii, I'm skipping over hyperfine interaction and the moments. And here I just show an example. So we have the radium isotopes here, and we see the isotope shift across the radium isotope chain. We can deconstruct that into a field shift and a mass shift, and we can extract then the charge radii, making some with some careful calculation or some comparison to other measurements. And this is where the details in the atomic physics come in, and we've also seen that before. We have to worry about the mass shift, and we can do that in a more I can show that in a more general way. We have our optical measurements, which we deconstruct into a field shift and a mass shift. We can compare those with the king plot method, which we've also discussed multiple times already. That requires input from other measurements, such as muonic atoms or elastic electron scattering, which requires some combined analysis of that data to then utilize the king plot method to then extract the field shift and the mass shift using these other measurements of the charge radius. Now that requires long chains of stable isotopes, so typically even Z systems and heavier systems. Of course, this type of analysis then breaks down if we only have one stable isotope, or in the case of the really heavy systems, no stable isotopes. And that then means that we then have to turn back to atomic theory to really give us a handle of the field and mass shifts. And that really then determines the overall accuracy of the charge radii that we can extract, especially as we extrapolate these measurements across larger chains. Okay, so that's more or less a sort of background starting point. You know, now we have the charge radii. What do we learn? What's the nuclear sort of side? So we can break this down into, I'd say, three general influences on the charge radius. So we have volume changes as we go across an isotope chain. As we add neutrons into the system, we expect the neutron wave function to expand. I mean, this is very naive, of course. And we would expect the proton distribution to also expand to minimize energy. So we would expect a volume change as we go across an isotope chain. And we would expect that to match the increase in the size of the nucleus associated with the increasing number of neutrons. We also are sensitive to the deformation changes and pairing changes. Now, you can see this when we present all of the data. We can see the effect of increasing or changing volume across the isotope chains. I show the heaviest region I'll talk about today. We can see the influence of deformation changes in the neutron deficient mercury and gold and platinum regions. And if we naively, or let's say in a very phenomenological way, model this with a a spherical nucleus and a deformation term, we can then relate the dynamic deformation that you associate with the mean square charge radius with other observables, which we can also then calculate or evaluate a value for beta, parameter beta, such as the quadrupole moment, and then interrelate whether or not we have a statically deformed shape or a rather dynamic system. What about pairing effects? Well, unless well understood, we can look at, or we see evidence of the influence of pairing from the odd-even staggering. So here I zoom in onto a completely different region just for clarity, and this is the copper isotope chain. And we can see as we go along a staggering, if I recast that using a 3-point filter, we can neatly see the staggering, the odd-even staggering across. And that is somehow influenced by pairing effects and cross-tail correlations. But what really is happening at a deeper level, I don't think anyone has a full description. And certainly a model description which reproduces the effect in mass and charge radii is yet to be fully resolved, and certainly is something which is a challenge, which would say that we don't yet really understand these higher order effects which are then affecting the odd-even staggering. And so what other influences? And so this is sort of an old story, which is the isomer shifts in multi-quasi-particle isomers. So this is the hafnium and ytterbium lutetium region. And these measurements are now nearly 30 years old. But what we see in these multi-quasi-particle isomers, in the case of ytterbium and hafnium, a large negative isomer shift. And with isomers, you don't have a systematic error associated with the mass, since the mass differences here between the ground state and the isomeric states are negligible. The isomer shifts really do look at the change in the charge distribution without having to be too concerned about systematic uncertainty associated with the mass shift. So this isomer shift here we see is significant, and very significant, much larger than the odd-even staggering in this region. I can recast that for the just taking a sort of filter so that we just see the volumetric increase, and then we can see the overall trend for all of these multi-quasi-particle isomers. And this is the 8- state in ytterbium, we got 23 half state in lutetium, the 8- and 16+ in hafnium. And we see just how large this negative isomer shift is compared to the overall trend in this region. So what's happening, and how is this influenced then by pairing correlations? So we can think, and this is a naive picture which I had presented to me during my PhD, and I don't think there's been much change in the overall description since then. But if we look at the ground state correlations across the ground state, we can construct a wave function spread of many states across the Fermi surface. So we have a very diffuse surface. When we go to these higher K isomers, the deformed alignment of these systems in the four quasi-particle states blocks out and reduces the pairing correlations, so we get a much sharper surface. So the overall mean square charge radius is less than the mean square charge radius for the ground state, which is much softer. And there have been some calculations done to try and take into account this effect. This was done by the Bordeaux group back in 2002. Without any pairing effects introduced into the calculations, they get a positive isomer shift for the excited states, and with the pairing correlations included, they get a negative isomer shift, which is smaller than that seen in the experiment, but in the right direction. Now, we should say, I'll just go back 2 slides. The interesting thing here is that the overall deformation, static deformation of these states stays relatively the same. However, of course, and unfortunately, especially in the hafnium case, the ground state being 0+ means that the comparing, it's difficult to compare things which we measure, say, with laser spectroscopy. We have to compare the quadrupole moments extracted from other methods. But what we see is a quadrupole moment that is largely the same, yet we have this very large change in the overall charge radius compared to the ground state and the overall trend in the region. So that brings me on to the features that we see across the whole heavy region of the nuclear chart. And again, this was pointed out yesterday. We see these strong kinks at the neutron shell closures. We see regular odd-even staggering across all of the isotope chains, which sometimes reverses, sometimes reduces in strength, and really understanding why we see that reduction in the odd-even staggering or reversal in odd-even staggering is not well described. We see also obvious shape effects, especially in the n=60 region and in the neutron deficient mercury. And another point, which is something which is often, let's say, overlooked, is the fact that the overall increase in the radii is much less than we would expect from, say, a naive 1.2 times a to the 1/3 that we see across or along the line of stability. So what does that mean? Well, I think then I'll leave that as an open question. And then I just neatly show where we are, let's say, the status of the laser spectroscopy measurements. So this is all measurements, charge radii and moment measurements. We see strong gaps in the chart of the nuclides associated with production and also difficulty. The hardest things are left till last, so that there's not just production at facilities, but also the laser spectroscopy schemes, the ability to study them in their ground state is sometimes difficult in the atom and the ion, and that then leaves us with these gaps in knowledge. Furthermore, we also obviously have gaps as we go out to the edges of stability due to production, and so then the effort in the field, and this is what the other tools obviously will highlight, is the drive for higher sensitivity and higher precision to push us out in these directions, and also to extract these values with higher precision in the future and answer these questions that we are raising now. So this talk, I'm going to focus on the region around the neutron-rich indiums, the copper, and also, well, it's not quite heavy, but the n=32 region. So the indium isotopes with a hole in Z=50 are a sort of classic textbook example of a well understood system, and the textbooks are Hyde and Crane, which give these examples. And the moment measurements across here sort of suggest that we have a reasonably good understanding. This is the magnetic moment measurements, but we have a remarkably constant magnetic moment right the way across the isotope chain of indium, which then allows a relatively simple description, not requiring a significant amount of collectivity, and reproducing it with sort of single particle whole plus vibrating core, with, I would say, a arbitrary quenching of the free particle G factor to reproduce this. The 1/2 state, I should add, is less well understood, partially because of mixing, so quantum mechanical effects, and also because of perhaps meson exchange currents and other things which the 1/2 minus state may would be more sensitive to. That's not to say that that's more to say that we don't understand what this state is doing as yet. So our recent work, we measured out to the n=82 shell closure. So these are the moments. This is the flat region, and then at the shell closure, we see a sudden and dramatic jump up, which is what you would expect at the shell closure, which is a good thing. However, it's much more dramatic than you would expect from the quenched value with a 0.7 times the free particle G factor. This is this red line that I showed on the other slide, and the actual magnetic moment of indium-131 is approaching then the actual free particle magnetic moment, and so significantly larger than the quenching factor, suggesting that our overall understanding of these nuclei is somewhat not so correct. And so these are the calculations which are presented here. I don't want to spend too much time on the moments, but this is more to point out this picture of let's say a region where there's not much collectivity, and the actual wave function of these isotopes is well pinned down, is not necessarily true. One of the things which I just want to point out to is the DFT calculations here, which reproduce the magnetic moment at the shell closure really well, without invoking any quenching or any, this arises naturally from the DFT calculations, which again is, in my opinion, quite an impressive result. But I'm just using that as a scene setter. So then I suppose I have two points I want to raise here. So when we compare the charge radii of the Indian isotopes across the chain, so this is the charge radii are shown here in purple. We have a range of calculations. So we have the DFT calculations shown in green, red, and light blue, shown across. And they're generally getting the trend quite well, but not quite getting the overall sort of fall over towards the shell closure. When we compare to immediate SRG calculations with two interactions, the 1.8 2.0 EM and the N2 LO GO interaction, we see again quite a large divergence from the actual overall trend. Now, these are preliminary calculations, so this isn't yet the full story, and I'm sure we'll hear more about this later, and there's probably updates from the version that I've been working from. But this is certainly, a preliminary status. If we use this three difference filter to assess the odd-even staggering, and then look at the odd-even staggering compared to tin, we see that the tin and indium isotopes have a very similar trend, with a reduction in the mid-shell and an opening up as the shell closure is approached, which is not reproduced either by the DFT calculations. And although the medium SRG calculations do show some evidence, well, let's say reproduce the odd-even staggering in the lighter isotopes, this reduction, this change as we go towards the N=82 shell closure, the trend is not really reproduced that closely. And so we might expect the medium calculations to reproduce the interactions in this region, or let's say the many body correlations in this region, but they tend to, or they are at the moment still failing to reproduce this the pattern that we see in the odd-even staggering as we go right up to N=82. And one of the things which I wanted to highlight here is the fact that the staggering in the masses is well produced by all calculations. And this is really clear here, that the masses, everything is doing really well. Yet when we look at the charge radii, this staggering of the charge radii is something which the theoretical calculations struggle to reproduce, suggesting that there is something missing at the moment, and more work needs to be done to really understand the role of pairing and the other influences on this staggering in the charge radii across the isotope chains. So we also measured two high-spin isomers in the neutron-rich indiums. So this is the spectra to prove that we did it. So this sort of fits into the story that I was discussing earlier in terms of the reduction in the charge radius when we go to a sort of a system where the pairing correlations are blocked. In this case, we're working quite close then to the N=82 shell closure. And from let's say a calculation point of view, we're in a much cleaner location to perform nuclear theory calculations, where a lot of the, let's say, many body effects in the hafnium and the terbium region are somewhat, let's say, reduced. So it should be a region where we can apply ab initio theory at the frontier, right up at the shell closure. Now, The calculations of the isomer shift in these two isomers, in 129 and 127, the ab initio calculations do get the negative direction, but they don't get the overall magnitude, especially in 129, which is shown here in purple. And although the scale of this is perhaps smaller than that which I showed earlier, the overall effect and change of pairing correlations between the ground state and the excited state is something which is yet not well understood. Okay, so I move quickly then to the next region nuclear chart. So this is the copper region, and this is again a reasonably old story, which is the impact of the tensor interaction, or the residual interaction on the proton single particle levels, the 1/2 and 5/2 state, as we start to fill the G9 orbital all the way across this. As the G9 orbital fills, we see a reduction in the energy of the 5/2 and the 1/2 minus, and at copper 75, this becomes the ground state. The 5/2 state becomes the ground state. At the same time, we have a reduction in the gap associated with the F7/2 also being attracted to the G9 as the G9 is filled, and then that raises questions on the overall strength of the nickel 78 shell closure, and measurements then are pertinent out here up to copper 79, where we can probe that with a single particle outside of the double shell closure. Now, we didn't get as far as copper 79, but we did push as far as copper 78. And with those measurements, we measured the charge radius all the way up to copper 78, and then extracted the odd even staggering. And there's some details about the overall the measurement sort of sensitivity that we required to do this, which was we were faced with only 20 atoms per second to make this measurement. But the sort of important point was that we could then compare this then with nuclear theory. And the nuclear theory calculations now in this lighter region are able, or were able to do a significantly say better job. So as we go to heavier regions, obviously the stretch gets greater. As we get to lighter regions, we start to see better agreement. The DFT calculations did very well at reproducing the overall trend in the charge radii, and we see this shown here on the top plot. But also the in-medium SRG calculations reproduce, I would say, remarkably well the change in mean square charge radius as we go from almost one shell closure right the way to the other. And the other thing which I think stands out to me as really impressive here is that the in-medium SRG calculations reproducing the reduction in the odd even staggering as the shell closures approached, and simultaneously reproducing the mass staggering, and also in the lighter regions. So the overall trend here, whereas the DFT calculations are not doing such a good job at all at the charge radii staggering. Either they're getting under producing it, or they're maintaining it very high as the shell closure is approached. So there's again something missing from DFT, but something is going right here. But again, and this just comes back is to the what is actually happening question. I can't answer that. And what is it that we learn from this staggering parameter, and what that tells us about what's happening in the nucleus as we approach the shell closure. And that really comes on to the next region of the nuclear chart, which is the n=32 region. So in this region, we have the new magic numbers at calcium 52 and calcium 54. And you can sort of, these are described in terms again of a reduction or a opening up of the n=32 shell gap as the F5/2 level systematically rises away or increases in energy as the interaction between the neutron F5/2 and the proton F7/2 reduces as the filling of that orbital reduces as we go down the isotone chain, right down to calcium 54. Now, The previous state of play in this regional nuclear chart was the calcium measurements up to n equals 32, and the potassium measurements up to n equals 32. So we have charge radii measurements up to the shell closure. And these already represent a challenge for nuclear theory to reproduce the charge radius of calcium, which is larger than the state-of-the-art calculations can reproduce. And that's kind of shown here. The experimental work shows the mean squared charge radius of calcium 52, and all of the other calculations, DFT, ab initio, couple cluster, are under reporting the overall size of this charge radii. Now that raises questions on our understanding of the increase in the volume of the nucleus as we move across an isotope chain, and also the overall effect of the shell closure on the charge radii at n equals 52. Just as an aside, so for this work we were studying the potassium isotopes, and in order to really pin down the charge radius, a key thing is to get the mass shifts pinned down and also the field shifts. And since potassium only has 3 isotopes to work with, its stability, that makes the job a lot harder to do with the methods I described earlier. So in order to, let's say, improve the overall accuracy of the charge radii measurements that we extract, we performed a sequence of measurements right the way across the chain of potassium, and worked in collaboration with Sahu to performed couple cluster calculations to extract F and M values with higher precision than we'd done before, allowing us to reevaluate and then produce the charge radius measurements with high confidence. So then when we compare the charge radii in the potassium isotopes to the theoretical calculations, we again use two models, one which the ab initio interactions, which expect there to be a shell closure at n equals 32, and DFT calculations, which don't explicitly expect there to be a shell closure at n equals 32. And what we see here is that the DFT calculations do a much better job at reproducing the overall trend, perhaps slightly higher volume staggering around the mid-shell following the calcium effect, but reproducing the overall increase as we go towards n equals 32 and beyond. So this is the new measurement at n equals 33. And we see that this is, again, without a significant kink in the charge radius. So at n equals 28 and beyond, we see a large kink here. As we go across the new shell closure at n equals 32, we see no kink. Now that raises the question, is that should we expect to see a kink with a shell closure, or is a kink something else that we don't really understand but is correlated to all of the other shell closures in the heavier systems? So when we compare this with the potassium measurement to the heavier systems up to iron, and I think this was also shown yesterday, including the nickel results, we see a trend which is almost identical for all these isotopes all the way up. Where the new potassium result is here, and we see no significant kink upwards linked to this shell closure. Now, that's not to say that this doesn't mean that n equals 32 is not a shell closure. What it means is that we don't see evidence for a shell closure from these charge radii measurements in the traditional kink that we see in the higher or the heavier systems. Now, if we are to, let's say, say that n equals 32 is for sure a double closed magic nucleus at calcium 52, then the fact that we don't see any evidence of a strong kink in the charge radii does really beg the question, what drives these kinks in n equals 28 and elsewhere? And in my mind, I don't think we have a real good understanding then of what's happening as we cross neutron shell closures and what drives these kinks. Oops. So that sort of brings me to my sort of remarks on the tool. I've just sort of highlighted those. And I think the key points that I wanted to make was that the simultaneous reproduction of charge radii and mass by theory remains a challenge, and I think I've shown you several examples of that. The kinks in the charge radii at shell closures are not well understood, and that was also raised yesterday by Wilfred's talk. The fact, or the increase, the volumetric increase of the charge radii is something which I feel is overlooked, and certainly why it is significantly less than a to the 1/3 is something that is also, let's say, a challenge, and I'm not sure really has been addressed. The other point which I highlight with the isomers is what is the role of pairing correlations in nuclei, and that is also related to odd even staggering and also the kinks. But I think it's clear that the charge radii provide a very important or rigorous test of our understanding of the internucleon interactions and many-body correlations and methods. And if we're getting them right, then it certainly provides confidence with the latest theories. But I think the observations that we have now certainly highlight in my mind that there's something missing from the current batch of interactions. And I also think, and that this is a comment which probably can be chewed over, is that we really need to think very carefully on how we define double closed magic systems and what we mean by magicity. If it's not going to be observable in all observables. And we should understand why we shouldn't observe it in each of those observables. So I also just finally thank the collaboration who are responsible for most of the measurements I showed this afternoon. That's the CRISP collaboration, and that's for the indium and the copper and the potassium work. And these are the PhD students are shown here in whose work I've been highlighting. And thank you for your attention.
Yep. Thank you for the excellent talk. Very impressive. And I think we might have time for one quick questions. If people want to ask questions, please raise your hand.
May I ask?
Yes.
May I ask?
Yes.
Thank you very much for your very interesting report. I have very simple question. Do you have the analytical formula, the force dependence on the distance between nucleons, protons, and neutrons in very simple nuclear, for example, deuterium nucleus?
I don't personally. That's my. So I think that's for the simplest system.
You speak very well about internucleon interaction, and so in this way, my question.
I think the issue is that if you look at the simplest system with just two body, such as a deuteron, you miss the influence of then the many body. So the starting point is more than two, and the influence of, well, I mean, this is a question to the theorists. I mean, there's clearly from the two-body interactions, we don't reproduce a lot of the effects that we see in the charge radii that have been measured. And we start to reproduce them when we introduce three-body and more, let's say, sophisticated interactions. So they start to come in. But are we really? I mean, is that a real effect, or is that a product of producing more and more sophisticated models? I don't. I mean, again, these are these are open questions.
Yeah, thank you.
Hi, everybody. And thank you very much for the nice invitation. I'm very happy to talk about the neutron equation of states from the mirror nuclei. Is it responding? Yep. Yep, okay. So the equation of states. Here I'm showing the cartoon or the schematic or the conceptual model of the equation of states. So this is the energy of the nuclear system as a function of the density or pressure of the system. And for the symmetric matter, meaning for the stable isotopes, where protons and a neutron have kind of same numbers, the system bind. So the energy goes to negative. And then once you change the asymmetry of the system, eventually you get to the pure neutron matter, neutron equation of states. And obviously, neutrons, don't bind each other. And the difference of these lines are usually called, symmetry energy or the symmetric energy. And that's the energy you gain, due to the symmetry of the system. And obviously, the understanding of the neutron equation of state is very important to understand the structure of the skin or the halo nucleus. And also, to have some sort of predictability of the structure of the heavy or even super heavy elements. And at the same time, understanding, the neutron equation of state is very important to understand, the astrophysical observables. For example, it is very important to understand, the signal from the gravitational wave, and also, to deduce, the size of the radii of the neutron stars. And again, this is just a conceptual model. And in reality, yeah, it moved. So in reality, the symmetry energy looked like this. So this is, some of the theoretical calculations, and the symmetry energy, actually goes all over. So it's very important to determine, experimentally some of the parameters. For example, the slope parameter at the nucleon saturation density to constrain theoretical calculations to be, extrapolated to the higher density or the lower densities. And then naturally, since the symmetry energy is not well constrained, the neutron equation of states also goes all over. Okay, so since the neutron equation of state has big implications to many fields of the physics, there have been many measurements performed. Heavy ion collisions, the analysis of the nuclear masses, isobaric analog states, and the signal from the gravitational wave is also a good source to understand the neutron equation of states. And among others, the neutron skin is known to be very sensitive to the neutron equation of states, and many measurements have been performed using many different probes. So the parity validating electron scattering, lead radius experiment obviously uses electroweak probe. Electric dipole polarizability, that's the response of the nucleons against the external electric field, is the electromagnetic probe. And the proton elastic scattering obviously uses storm forces to probe it. And the take-home message from this slide is what I'm trying to say is more or less all the L measurements are model dependent. So since I'm talking about the neutron skin, here I'm showing the root mean square radius. So here the density is shown as a function of the radius, and the density distribution typically look like this with some tail. And the root mean square radius is defined somewhere here. And this density distribution is basically for the stable isotopes, where the protons and the neutrons numbers are about the same, so their densities kind of overlap each other. Once you go to the neutron-rich nucleus, there will be excess neutron in the core. And of course, the density of the core saturates, so the neutron, has to seeps out, extend, towards the outside of the nucleus. And now we can define the neutron skin. That is defined by the radius of the neutrons, root mean square radius of the neutrons minus, protons root mean square radius. And here, neutrons cannot seep out, as much as it wants because it changes the energy, the density, of the core as well as, the tail. And that changes the energy of the system according to the form of the equation of states. So, there has to be some sort of happy medium. So that's why, neutron skin thickness is very sensitive to the form of the equation of states, especially for the slow parameter L at the nucleon saturation density. So here I'm showing, how experimental measurement is translated into the, the neutron skin. This is a result of the PREX measurements. And this is, the parity violating electron scattering measurements, taking advantage of the fact that neutron carries most of the weak charge. So essentially, this measurement, this experiment measures the neutron distribution inside a nucleus. So what this experiment measure is the parity violating as asymmetry parameter, and this is the model independent measurement. And then once we translate this information into the neutron skin, we need help from the theoretical calculations. The model dependence kicks in. So here they show the bunch of theoretical calculations, and that shows very linear trend in a nice correlation. And using this correlation, the experimental information can be transferred to the information about the neutron skin. And then the neutron skin information again is correlated through many theoretical calculations to the size of the slow parameter L. So this is typically we deduce the information about slow parameter from experimental measurements. Another example is the electric dipole polarizability. So that's the response of essentially the protons inside a nucleus against the external electric field, Kulik's experiment or something like that. And again, there is a density distribution, and this is where the equation of state kicks in. And basically, the L parameter works as the restoration force, to pull the protons back to the original location. So there have been several measurements. This is a result of the lead 208. The bottom part shows first measurement of the radioactive isotopes, nickel 68, and they do kind of same thing. Experimental measurement is correlated using theoretical calculation to the neutron skin thickness. And a little later, it's been shown that the products of the dipole polarizability and J, I think J is the amplitude of the symmetry energy at the nucleon saturation density, has kind of strong correlation to the size of the slow parameter. Okay. So the point is, all the measurement of L are model dependent, and it's very important to have, a variety of different, physics observables to cross-check the model dependencies, from different aspects. So I'm here in my talk, I'm proposing to use the, charge radius. Okay, so let's assume, the charge symmetry is perfect, and then the neutron's radius of a nucleus is equal to the proton's radius of its mirror nucleus. Okay. So this is original definition of the skin thickness, neutron skin thickness. That's the difference of the neutron's radius minus protons, charge, protons radius. Now I replace this relation with the difference of the mirror charge radii. So this is the electromagnetic probe, and also we can do model independent determination of the charge radius. So Alex Brown, first came up with this idea and did some calculation for the pair of the nickel 54 and iron 54, and a difference is calculated as a function of the L slow parameter, and all these marks are the calculations based on the size of the lead 208 neutron skin thickness of the lead 208, and these calculation already includes the Coulomb interaction back in. Without Coulomb interaction, all these points kind of line up in a straight line. Okay, so now if we determine the difference of the mirror charge radii by experiment using this relation, we can get the size of the slow parameter as other experiments do. In this paper, Alex also came up with that the difference of the mirror charge radii is correlated with the difference of the numbers of the neutrons and the protons, essentially in an isospin. So once the isospin gets bigger, the slope of this correlation gets steeper and steeper and steeper, and that means it is less sensitive or the less susceptible to the systematics of the theoretical calculation and in experiments. And also, it is going to be more sensitive to determine L. So in my presentation, I'm showing the result of the nickel 54 radioactive and the iron 54. This is stable, whose radius have been determined precisely in a different measurement. And N-D, is of this system is 2, and this is not that big. So the largest we can hope to have of all the mirror pairs, throughout the nuclear chart is 6. So the current system is not that sensitive, and our experimental measurement has to be very, very precise, which is possible, for the charge radius measurement. Okay, so experiment was performed at the National Superconducting Cyclotron Laboratory at the Michigan State University. We use, the cyclotrons to accelerate the primary nickel 58 beam up to high energy, impinges on a production target, and produce nickel 54. And produced nickel 54 was selected from many other reaction products using the A1900 fragment separator. Then the prepared nickel 54 was first transported to the gas stopping system, where the fast nickel 54 beam was stopped, thermalized, and extracted at low energy, around 30 kilovolt total. And then from here, the low energy beam was transported to the laser spectroscopy beamline here. And this was the layout, until last year. And now we are moving towards the new facility. That's the facility for the rare isotope beams, FRIB. So the old facility is shown in the upper part of this, new figure. And the old cyclotrons were used to be installed, around this corner here. And they were already replaced by much larger scale of the linear accelerator here. And that will give us much wider range of the access to the radioactive isotopes, and hopefully give us, more opportunity for the discoveries. And the first beam is scheduled actually in next month, this year, May 2022. So we're very excited about it. And if you are interested in running experiment at FRIB, there is a nice website, that gives you the estimate of the production rates of your favorite isotopes. Okay, let's go back to the my experiment. So this is a laser spectroscopy system, Bekola. In this scheme, the radioactive beam is coming from top, first injected into the radio frequency quadrupole ion trap. So the DC beam was converted into the bunched beam, pulsed beam, and then bunched beam was transported to the collinear laser spectroscopy beamline, where the laser light is collinearly overlapping with the ion beam for the bunched beam fluorescence measurement. Okay, so I'm jumping into the result. So this is a result of the nickel 54 hyperfine spectrum. We measured it relative to the nickel 60 stable isotope. So the experiment was done with 15 atoms per second. This is pretty low as a fluorescence measurement, laser spectroscopy within fluorescence measurement. You can tell that from the size of the error bar and also the scatter of the data compared to stable isotopes. However, we can precisely determine the centroid. Okay. So from the isotope shift, we can determine the differential mean square charge radii in the radius and required atomic factors, copper and F, or evaluated using the King plot analysis. And we also need the absolute charge radius for nickel 60, that's the reference isotope, and the mirror nucleus, iron 54. And both were evaluated using the combined analysis of the muonic X-ray and also the electron scattering data. And we determine, our result like this. And the result is plotted here. So as a function of, the L. And our present result is shown in a gray band that includes the systematic error. And all these marks are the theoretical calculations, and that shows the linear trend. And the dashed line around the theoretical calculations are the systematic uncertainty from the theoretical calculations. And from this correlation, we can determine the size of L within this red band. So our result indicates soft equation of states, meaning small r radius of the neutron stars. And our result is also consistent with the gravitational wave signal from the binary neutron star merger GW170817, and also the result from the P-Rex 2. However, within 1 sigma error bar. However, P-rex2, likes to point to the stiffer equation of states, larger L. Again, I understand this is 1 sigma error bar, but why, the reason why I'm saying this is there is other paper recently. So they look at, a bunch of different, theoretical analyses and other experiments, and, most of, many of, these analyses, line up to the smaller side of the L, soft equation of states. And our result is, plotted, at the bottom of this figure, and that is aligned with, the smaller side compared to the, the P-rex, results. So, it's not definite, but, there might be something systematic happening. And now we know C-rex experiment has been completed. That's the neutron skin thickness measurement of the calcium-48. So because of this, discrepancy, I think it's very interesting how the C-rex result, comes out. And actually, our present result is sensitive to the neutron skin thickness of the calcium-48 as well. So our theoretical calculation, lines up in a straight line, showing nice, correlation. And from our measurement, we can determine or predict, the size of the neutron skin thickness of the calcium-48, and it comes out, this number. And this is definitely smaller compared to the lead-208. I don't believe, the C-rex result, has been officially published, but there was the DNP talk, last fall, and they show, preliminary analysis. And that comes out, inconsistent. It looks, inconsistent with the P-rex, result, lead-208, results. So I think at this point, it's very interesting to see, how the C-rex, result comes out. We did kind of similar measurement for a different mass system. This is a calcium-36 and a sulfur-36 mirror pair. And I don't want to repeat the same thing, but the take-home message from this slide is, the present measurement and the previous measurements are consistent in terms of the slope parameter and also the skin thickness prediction for calcium-48. So our experiment comes out very excitingly, so we were happy about it. However, like I said, all the L measurements are model dependent, and it's very important to assess the model dependence. So as an example here, I'm showing the result of the calcium charge radii chain together with several theoretical calculations. And the first one is the typical EDF calculation, SV min or Skilm type EDF. And if you look at this line, it does not reproduce the local variation of the charge radii at all. So in that sense, this is no good. So this spherical calculation required some sort of corrections, like the quadrupole deformation correction or something like that. And that's the model we use for the present analysis. Okay, there's another one, the defiance EDF, which is shown in yellow. We listened to a very nice talk from PG on Monday, and this EDF contains novel density gradient dependent terms in pairing term and also the surface term. And this addition makes this EDF so successful, not only for the calcium isotopes, but for other elements like we saw in the previous talks. And the other point is the treatment of the proton continuum effect. Since we're dealing with a mirror partner, mirror pairs, and one of the pair tends to be very close to the proton drip lines, and where the proton continuum effect is very important. And that is kind of shown, between in two lines, gray line and a yellow line. Gray line is the BCS calculation, and it is known that the BCS calculation gives us unphysical results when it get closer to the proton drip line. And HFB formalism is the right formalism to use for the proton continuum effect. So I'm going to get to each point briefly. So let me start from the present, model we used in the analysis. So I call it, kind of beta 2 model. So according to the Bohr collective model, charge radius is something to do with the deformation. And let us, constrain ourselves and limit ourselves to the quadrupole deformation, beta 2 squared, because, this is anyways, has a dominant contribution. And then, this, deformation parameter can be obtained experimentally if the reduced transition probability of the E2 transition is known, B of E2. So the spherical EDF calculation can be corrected, using the experimental input. So here in this figure, I'm showing the charge radius as a function of the proton number for the N equals 28 isotones, starting from calcium 48 up to nickel 56. And all these circles are the exponent. And the straight line connecting calcium 48 and nickel 56, which are spherical, is the line for the spherical nucleus. And obviously, all the experimental measurement deviates from this spherical line. And we performed the theoretical calculation taking the spherical EDF corrected by the beta 2 deformation, and that are shown in red crosses. And these red crosses reproduces the exponent very good. So this is the model we use in the present analysis. And I would say this is a very specific model tuned to the specific region of the nuclear charge. And more is discussed in a recent paper which has been submitted. We're going to see it in archive soon. And just for fun, here I'm showing the global behavior of such model. So here I'm showing radius as a function of the neutron number for many different elements. So the top panel shows the spherical calculation, the difference of the spherical calculation from exponent. So as you can see, the spherical EDF does pretty good job for the magic nucleus. However, in between, there's huge deviation. The middle panel is the theoretical calculation, EDF calculation, that contains the beta 2 corrections. So, top and middle panel resembles, pretty good, almost similar. Of course, the bottom panel is the difference between these two panels, the top and middle. So the take-home message of this slide is, most of the large deviation can be explained, experimental and the spherical EDF deviation can be explained by the beta 2 correction. And of course, here and there are, little small, deviations, but that's whole different stories. And that is discussed in the new paper. Now I'd like to talk about the affinance model. So again, we listened to very nice talk on Monday from PG. And the affinance model does include, the new, very rich density-dependent, pairing terms. And they performed the calculation for the coefficient of the determination to see the correlation between skin or the mirror charge radii against, the slope parameters. So if you look at the result of, the skin, it shows an almost one-to-one correlation, very, very strong correlation between skin and L. However, once they calculate, the correlation for the mirror charge radii, let's look at, that just, orange or the pink ellipsoid. They see, looser correlation. The coefficient of determination is only 0.7 compared to 1. So this means, the mirror charge radii is less correlated compared to the skin, to the L, and it has contribution from some other part of the EDF. And that is shown in the right-hand side of the figure of the bottom part. So the pinkish color is for the skin. So as you can see, skin is mostly correlated with the symmetry energy. However, if you look at the bluish color, that's for the mirror charge radii, it has, lots of different contributions from different, part of the EDF. And it's interesting to see, if you look at the finance EDF, now the skin has, some other contributions, from other part of the EDF. So, so the take-home message of this, the publication is, because of the large uncertainty, theoretical uncertainty, it is difficult to set stringent constraint on L, even if exponent is determined precisely. Using, this sort of, global fit model, which has, rich pairing interaction. So now I want to talk about the proton continuum effect. So they did, a bunch of calculation again, and I just want to focus on, this pink region. So they perform, BCS and HFB calculations. Like I said, BCS calculation is known to give us, the unphysical, result for the charge radius when it gets close to the proton drip line. And the HFB is the right formalism to use. So let's look at, result of nickel 54 and iron 54. So both calculations give kind of similar number, which is consistent with experimental measurement of the difference of the charge radii. So this means for this pair, the proton continuum effect doesn't play important role. On the other hand, if you look at calcium 36 and sulfur 36, calcium-36 is much closer to the proton drip line. And they do see, some differences. So, for this system, proper treatment of the proton continuum is important. Although, their error bar is touching and the exponent, somewhere in the middle. They also perform the calculation with, 0-point vibrations, which is shown in, open squares. And that shows, the deviation from the spherical calculation, for this spherical finance, calculation, it is important, it might be important, to take into account, the deformation effect as well, although they do not put error bar on this, point. Okay, so I'm not trying to judge anything here. So I just, try to emphasize that, all the L measurements are model dependent. And it's critical to have, variety of experimental observables to, cross-check the systematics from different aspects. And mirror charge radius is, only one of them. And again, I would like to emphasize that, more experimental and the theoretical investigations are encouraged here. Okay, so as a summary, we determined L from the mirror charge radii, and our L is consistent with the P-rex and also the gravitational wave signal indicating soft equation of states. However, P-rex points to the stiffer equation of states. And we can also predict, the size of the neutron skin of the calcium-48, and that is smaller compared to the lead-208. So at this point, it's very interesting how the C-rex result comes out. And as a future, we have, one complete pair, silicon-32 and argon-32, and analysis is ongoing. And any atomic calculation help for the atomic factors from the theorist is, appreciated, especially for silicon. And we're also interested in going to the more sensitive systems like nickel-52 and chromium-52, oxygen-22 and silicon-22. And for those nuclei, even at FRIB, the production rate is very, very small. So the way to go is to perform RISE. RISE is a new system, resonance ionization spectroscopy experiment, RISE. So this project is, driven by MIT, and we just added, the extension of the beamline, new beamline to the existing, Berkeley facility. And the plan is, we have just installed, the new extension here, and the plan is to commission this part of the beamline over the summer, and I hope to get the beam from FRIB towards the end of this year. And the first experiment is going to be aluminum, and for aluminum, we need, atomic calculation input from the theorist. We also have, approved experiment on thorium as well. And this is not everybody, but, part of the collaboration. Okay. Last but not least, these are the collaborators, and thank you very much for your attention.
Yeah, thank you. Thank you for a very nice talk. And any questions from the audience? Yeah, if anyone has a question, please just unmute yourself and ask your questions. You can also raise your hand. Yeah, maybe I have one question. So you said the correlation between the the charge radius of mirror nuclei and the slope parameter might not be clear, right? I mean, that's from.
Well, yeah. So what I said was, there's a model dependence. So in this model, beta to model, we see clear correlation. But once we include, the rich pairing interaction here, we lose, the strong correlation. But there is correlation. It's not one. It is still related to the L. So their claim here in this paper is it's not possible to set a stringent constraint on L. And what does stringent mean? So this is the constraint we set for the equation of states in our model, which has plus minus 30, plus minus 50 error bar. Is it stringent? Probably no. So at this level, it doesn't matter. But once you get to the much tighter constraint, maybe charge radius, mirror charge radii is not good because of the uncertainty in the model. Well, I think this is under discussion.
Okay, but it's a density, energy density functional theory only, the only theory that can provide correlations between these two observables, or can ab initio theory also provide some correlation plot like that?
Yes, they do actually. So in the previous measurement, open circles are, the ab initio calculations. But the thing is, ab initio calculation comes up, one number, cannot do, the correlation. They cannot change the parameters. They calculate, these numbers for different parameterization, but cannot calculate, this as a function of L, because L comes out by itself. That's ab initio. Yeah, but it is possible. They can calculate it. And yes, if there is some other, theoretical framework, it is very, very much, welcome.
Okay, so any other questions? Okay, if not, so thank you. Yeah.
All right. Yeah, thanks, Lucas. Thanks to the organizers for inviting me and giving me an opportunity to kind of give an update on some of the things that have been happening, although you saw quite a few results that have been produced with flavors of the IMSRG in the talks in the morning session, or in the first session this morning. So I want to start my talk with this updated version now of what I lovingly call my propaganda slide that shows the progress that ab initio calculations have made in covering the nuclear chart. And by covering the nuclear chart with ab initio calculations, that doesn't necessarily mean that we're already perfectly accurately reproducing experiment, of course. But these are nuclei that are now within reach of ab initio methods, and for which we can now possibly make meaningful contributions to the analysis of experiments as well. And you will notice, if you know the previous version of this chart, it stopped kind of in the tin region, but as of December last year, lead 208 has actually been added. So there has been progress in how to handle the 2 and 3 nucleon forces in these heavy nuclei and to remove basis truncation artifacts that will allow us now to really, really push up into this, region of actually heavy nuclei, let's say. Okay, so the tool that we're using is the multi-reference, possibly in medium similarity renormalization group. And I have listed quite a few references there in case you want to peruse them and read up on some of the stuff that I'm just going to sketch here. So the problem that we're facing in any many-body theory really is this exponential wall that comes from the growth of the many-body basis size of the Hilbert space. So if you want to perform an exact large-scale diagonalization, you will be limited to very light systems. Let's say here in this case, nuclei up to the lower SD shell, where matrix dimensions approach like 10 to the 10 times 10 to the 10. So obviously you will not be able to construct that matrix and store it in memory, even though it is very, very sparse. So on this right plot here, it shows just the number of non-zero matrix elements. And you see that that is closer to 10 to the 12, not 10 to the 20 in this extreme case. But then you also notice that actually, if we include 3-body interactions, as we know we have to do in our low resolution description of nuclei, then the matrix gets significantly less sparse than if we had 2-body interactions alone. So one can devise means of dealing with that, let's say through importance truncations of the basis, but they cannot fully compensate this exponential growth either. So the idea that we're using in the IMSRG is that underlies really any kind of renormalization group. And it's very parallel to how you would define other similarity transformation techniques. The idea is to perform a transformation of the Hamiltonian in operator form that will then guarantee that the structure of the matrix in many-body Hilbert space is going to be simplified. And the way we do this is we choose a reference state for the purposes of this example, just a simple single Slater determinant. whose with single particle levels filled up to the Fermi energy. We construct all particle hole excitations of this state. We normal order our Hamiltonian with respect to this reference and kind of organize the basis in terms of excitation energy that way. And then what we want to do is we want to perform a unitary transformation that smoothly transforms this matrix that's shown on the left-hand side. So this band diagonal matrix where the reference state is coupled to two particle two-hole excitations in case we have a two-body interaction, or maybe three particle three-hole excitations if a three-body interaction is present, into this final Hamiltonian that's shown here on the right-hand side, where this upper left block that contains the reference state is really decoupled from the rest of the spectrum, which would then mean that we have extracted an eigenstate and an eigenvalue of the Hamiltonian, right? If there is no way to excite the state into the other, into the orthogonal complement of it. And a nice benefit of this transformation is that in the process, you will actually also eliminate outer diagonals of this Hamiltonian matrix. So the Hamiltonian really gets simplified just from a structural perspective when you run this transformation. Now, from a physics perspective, what we're doing is we're shuffling correlation out of the wave function into the Hamiltonian itself. We are RG improving it. Technically, this process is done by writing the transformation as an operator flow equation that's given right here, where we have this generator eta that can be commonly defined by splitting the Hamiltonian in what we call diagonal and off-diagonal pieces. And that really just means that diagonal is what we keep as we evolve, and off-diagonal is what we want to suppress as we evolve. And as I just told you, we want to eliminate the parts of the operator that couple the reference states to these one particle one hole and two particle two hole excitations in this example. So this will define our off-diagonal Hamiltonian, and that gets driven to zero as we evolve. And when we do that, if you plug these normal ordered operators into the commutator here, you will actually create induced higher body terms, which in a way is just showing that when you're dealing with a many-body system, what you would call two-body and three-body and four-body forces is really scale and scheme dependent, right? Because you can always perform unitary transformations and reshuffle these things around without actually changing any observables, because you're doing unitary transformations. Well, you would not change the observables if you did everything perfectly. But of course, to handle this, we cannot deal with up to A-body interactions. It would be doable at polynomial cost rather than exponential cost, but a polynomial with a high exponent is still pretty terrible from a computational point of view. So what we have to do in practice is we have to truncate all our operators at the two-body level in practice at the moment. And then going to three-body operators, three particle, three-hole like correlations will be like the next big major step for us. So I want to talk briefly about the idea of the reference state. So when we use the standard signal Slater determinant, as I mentioned, we essentially say that the IMSRG transformation has to describe all the correlations in the system, because the Slater determinant is essentially an independent particle state. So that means if you want to describe correlated pairs or triples or quadruples, quintuples of nucleons, it's up to the IMSRG transformation to do that. And then you would really need to include, let's say, up to 5-body operators, which would cost us like, well, that would raise the exponent, I think, to a factor 15. So n to the 15 scaling is not great. We want to avoid that. And the nice thing about the IMSRG framework is that it actually gives us a means of doing that. So you may ask, why should I worry about these complicated correlations? Well, we're dealing with nuclei, and nuclei are known to intrinsically deform because they have strong correlation effects, and these types of correlations are collective in nature. So they would involve certainly more than 2 or 3 nucleons at the same time, albeit that all of these nucleons are not necessarily excited to very high energies. So whenever we deal with nuclei that really have collective excitations or collective features, this standard reference state choice may not be enough. But in the IMSRG, we can actually work with states that already have some correlations built in, right? And in this case, what we can do, we can take a reference state that contains collective correlation and then build the few particle so-called dynamical correlation where a few nucleons get excited to very high energy and include that on top of the statically correlated reference or the collectively correlated reference state. So in this way, it gives us a handle to actually treat both of these types of correlations, which are important in nuclei. And we may be able, as indicated by the name that I've given this whole approach here, to do so at the cost of a single reference calculation that would otherwise just scale as n to the 6, would otherwise only include doubles like or two particle two hole correlation in the framework. Now, that allows us then to really define what I would call IMSRG improved methods or hybrid approaches. So you use your favorite many-body method to define a reference state with some correlation included. You perform an IMSRG evolution of all the operators, and then you take the resulting Hamiltonian and perform method XYZ again to extract all the observables that you would like. And possibly you could think of adding self-consistency to that and then just iterate and take the solution that you get at the end from your favorite many-body method and use that as a new reference state. Indeed, we have actually at this point almost a family of methods that are IMSRG improved at hand. So this what you know as the standard IMSRG from the original publications, IMSRG for closed and open shell nuclei. You could also call as in medium Hartree-Fock for short, or in medium projected Hartree-Fock-Bogoliubov, which means these are Hartree-Fock or projected HFB calculations with IMSRG improved operators. You heard in the morning about the valence space IMSRG, where IMSRG transformations are used to derive shell model interactions, and you're performing valence CI. There's a full CI version of this, the in medium no-core shell model that we developed in 2017 already. And the method that I'll mostly be talking about today is the in medium generator coordinate method that really is appealing because it tries to combine two types of expansions, namely the particle hole-like and the geometric picture that you have in the GCM. So why is this not progressing? Okay. First, a few words about the valence space IMSRG. So the merger of in medium SRG with CI methods. You can look at this recent review that was led by Ragnar Stroberg. And here I'm just giving you like a kind of an overview of what this method can achieve and how it relates to all kinds of other ab initio approaches. So these are just isotopic chains from like carbon, nitrogen, oxygen up to nickel. And you see that if the same interaction is used in these calculations, so chiral 2 plus 3 body forces, then essentially all of the ab initio approaches are giving consistent results within the scales that are given here. So typically it's like within a few percent of each other, you will find the ground state energies agree. And if you use the valence CI as like the driver or the framework to apply your IMSRG evolved Hamiltonians and operators, the nice thing of that is that, of course, you have easy access to the entire spectrum and also to odd nuclei that way. So you will see that odd nuclei are included in these chains here for some of the methods, and in particular for the valence space IMSRG. Of course, we don't want to stop just at energies, so one can look at other quantities like radii, which is possible in this valence space IMSRG framework. Or you can look at transition rates. So there was this nice paper from a couple of years ago at this point already, where valence space IMSRG and coupled cluster no-core shell model were used to kind of explain the empirical quenching that is needed to explain the Gamow-Teller decays in the SD and PF shells. So in these empirical calculations that are shown for various transitions in orange, with empirical interactions, you need to introduce like an empirical quenching factor on the axial vector coupling GA. That's usually like 75 to 80%. And if you instead use an unquenched GA and just do a good job at treating or a better job at treating the many-body system, the many-body correlations, namely by doing valence space IMSRG and including two-body currents, you can explain pretty much all of this quenching. There are still a few outliers that are probably related to the fact that these calculations were still done with a valence space IMSRG 2 truncation. So that has to be possibly then revisited with a valence space IMSRG 3, and hopefully then one will be able to explain these discrepancies. However, not all transitions are described equally well. So I'm indicating that kind of in this figure that's also a bit dated by now. There has recently been, like just a couple of weeks ago, a paper on the archive and in PRC by Ragnar Stroberg, where this is updated and looked at more systematically for SD and PF shell nuclei. But the message here is that while the valence space IMSRG and another flavor that does not introduce a core actually do reasonably well on 2+ excitation energies in these nuclei shown here, the BE2 rates are actually significantly underestimated. I want to direct your attention though to the oxygen 22. So in this case, in a standard shell model, you have a pure neutron valence space. And in an empirical calculation, you would need to introduce an effective charge to produce a BE2 transition in the first place. Now, in the IMSRG, what happens is that the one-body transition operator is being transformed and the effective charge is generated for you, except that it's not strong enough to really explain the experimental results. So there are pieces of the operator that were missing because of the truncations and because of the missing collectivity in the reference states. Because remember, valence space IMSRG 2 essentially deals with a particle hole-like, few particle, few hole-like excitations that get built into the operator, but then it relies on the valence space CI to produce all of the rest of the possible collectivity. And clearly in this combination, we're not getting everything that we should be getting for static correlations. Another example of that, this version of this figure was shown in Tieren's talk in the morning. This is just a ground state calculation without a core of the charge radii of the calcium isotopic chain. And you notice that this inverted parabola shape between calcium 40 and 48 is missing, which is in the shell model explained by configuration mixing between 4-particle 4-hole excitations into the PF shell. So that would also be a static correlation effect. Or as you heard from in Kay's talk just now, it's associated with quadrupole deformation. So it's really, or quadrupole correlation, so it's really missing collectivity that drives this. So what can we do to capture the missing collectivity? Well, I said we're going to look at the GCM because that uses a geometric expansion, and we're going to try and combine that with the particle hole-like expansion picture that the IMSRG is formulated in. So as a starter, I'm showing you some data here that is already quite a few years old, and we're working hard on getting that out sooner or later. This is a calculation of the meta radii, actually, of the magnesium isotopes using a chiral 2- and 3-body force and different flavors of methods, let's say. So the green line here is just essentially a spherical calculation, a spherical projected HFP calculation. Then you see if you go to the blue curve, and perform a GCM calculation with this chiral Hamiltonian, you somewhat improve the meta radii, but the trend of experiment is actually not reproduced. So this looks not quite right compared to the experimental data. But then if you do this combination of IMSRG improvements with the GCM, you actually get the trends fairly well, in particular the bending of the curve. And this is just illustrated if you scale up this curve by 6% or so, then you land on top of the experiment. But of course, that's really only for one particular chiral interaction with one particular set of cutoffs. And what one really should be doing now is like a variation of the cutoffs to kind of map out a band and to see how that compares to the experimental data. So we clearly get improvement from these collective correlations or the combination of dynamic and collective correlations in the IMGCM. But there is this deviation, or there are these global shifts, or sometimes kind of like rotations of the trends around the pivot that we know now to associate with variations of the cutoffs of the input interaction. And you can also actually see evidence of that when you go to Kieran's talk from the morning. Let's say in the calcium example, he showed a plot from this, the original publication by Ronald and collaborators, where various chiral interactions were used. And you see that the trends are pretty much the same, but the cutoff variation just shifts them up or down in radius. Now, eventually, if we can improve the many-body side, then the bands that come from the cutoff variation of the chiral interaction, they should shrink down more and more. So we need to have an eye on both of these aspects as we go forward, so that we can really make meaningful contributions to experiment. The other thing that we looked at here, or what actually originally drove this, was also an investigation of the BE2 values. So as I mentioned, we had missing collectivity in the valence space IMSRG alone. And you see, if you focus on this right panel here, that you actually, I think incidentally, are pretty much in agreement with the experimental data there. In fact, it's a bit too good, because we know that this interaction underpredicts the charge radii, right, as we saw, by 5 to 6%. So you shouldn't probably lie exactly on top of this curve. Plus, there is this effect on the 2+ energy in magnesium, what is it, 30, that is over-predicted. But we believe we understand that now. This is essentially that in this nucleus, the IMSRG evolution tunes the calculation or the Hamiltonian too much for the ground state rather than for this excited state. That's something that we'll see on another slide in a second. But the message here is that we get much improved BE2 values from this method that captures both dynamical and static correlation. And as a technical or consistency check, if we look at the transformed or evolved quadrupole operator, we actually see that with the GCM reference state and in the IMGCM framework, the bulk of the effect will be a transformation of the one-body operator. The induced contributions are found to be small, on the order of 5% or so, whereas in the valence space IMSRG, they are essentially at least as important as the transformed one-body part. And again, for that, I refer to Ragnar's recent paper. Now, I mentioned this effect on the 2+ energies. So we saw that as well in these calculations with the French group and Seiya Saclay, so Thomas Duguay and collaborators, where they have developed a new perturbative method that uses GCM states as input. So you can perform perturbation theory on that to recover missing correlations. And we combined that with IMSRG improved Hamiltonians. So this left figure shows the absolute energies of the neon 20 ground state for different methods, starting from just symmetry restricted Hartree-Fock and breaking symmetries, so allowing axial deformation, forms of standard perturbation theory or Bogoliubov perturbation theory for open shell nuclei actually. And then this black circle, that's like projected GCM. And then you can perform a perturbative enhancement to go to this red star, the PGCM with perturbative correction that brings you close to experiment. But now I want to point out that if you perform this with an IMSRG evolved Hamiltonian, that's indicated by this value S here, this is the flow parameter that controls how far you have evolved, you actually see how correlations are reshuffled and how the effect of including these perturbative corrections gets smaller and smaller because they have been built into the Hamiltonian in the first place. And you're starting out already with restricted Hartree-Fock much closer to experiment when you do the calculation with this RG improved Hamiltonian. But then if you look at the spectrum, you see that, well, the 2+ energies are quite stable actually once you do the IMSRG evolution and this perturbatively enhanced GCM. But for the 4+, we're not able to make the result fully as independent. So that is an indicator that some correlations are still missing, because if we had a reference state and an IMSRG evolution that are sufficiently complete, let's say IMSRG3 and a rich reference, then the evolution for particular observables should be unitary, and you should not get any S dependence anymore. And you see that this is true for the 2+ excitation energy, more or less here. So this is actually very nice, because it means that the IMGCM comes with a built-in diagnostic tool. We have the flow of the flowing Hamiltonian and operators available, and we can actually use them to analyze. Yep, we can use them to analyze how much we violate unitarity or don't violate unitarity. And this is something that's not possible in the standard phenomenological GCM, where you would be using empirical interactions or density functionals as input. However, it indicates that we are still missing some correlations. So as I said, either a richer reference state or IMSRG3 is necessary. So in this figure, I'm just going to show you what a richer reference state can do. So this is the low-lying spectrum of titanium-48. The first one is done with just an axially deformed reference. The second one includes cranking to have some timeout fields in there, or timeout correlations in there. And you see that the spectrum is actually compressed that way. And what was very striking is that if you perform this in medium full configuration interaction calculation for growing model space size, you see that the two calculations are actually consistent with each other, and they are evolving towards consistency with the experimental excitation spectrum. And unfortunately, I don't have the BE2 values for the cranked case, but I think they also get improved. I saw that Jiangming is in the audience, so he may be able to comment on that. So a richer GCM state is one way of improving, or possibly then adding more IMSRG correlations. I'm going to be very brief here. So we calculated titanium-48 because we wanted to look into the neutrino-less double beta decay of calcium-48 to titanium. We computed the matrix element. In fact, a bunch of groups did this calculation. And at this point, I would say we find consistent results if we use consistent interactions and transition operators. But there is a lot more work to be done to improve the truncations, explore additional GCM calculations, include currents in the calculation, et cetera, et cetera. And then, of course, the big goal is to do this for germanium-76, which is in progress at the moment. So looking ahead, here is kind of my shopping list for the next couple of years. So I mentioned already the inclusion of IMSRG3 correlation. So the framework, the equations and everything is derived. And in some cases implemented, but this will be a numerically challenging calculation, where you go from using single nodes in IMSRG2 now to essentially going to leadership class machines. But it's necessary to do that because we needed to really assess what the many-body truncation error in the IMSRG is. And to, as I said, to do this combined study with the cutoff variation to see whether cutoff bands shrink and whether that can shrink down enough so that experiment can give meaningful feedback on the interactions and what might be missing in them. Now, to help with the high computational scaling, we're looking into tensor factorization, so exploiting low-rank structures in the interactions. Another big thing is that the IMGCM in this no-core formulation is built around projected HFB states. With angular momentum projection and particle number projection, and extending that for odd nuclei will be an important thing to do, but it's also kind of challenging and will make them the calculations also even more expensive than they are right now. But it will be necessary to tackle nuclei for which valence space IMSRG would become either difficult or prohibitively expensive if you have to go to multi-shell valence spaces, which is going to be a very realistic occurrence if you go to the exotic neutron-rich domain that EFRIB is going to open for us. UQ and sensitivity analysis is a big thing. And for that, you need to do lots and lots of these calculations. So we need cheap surrogate models, so emulators, in other words. And I hope that I will have some good news on that within a month or so. So we think we made a breakthrough, and there may be a paper in the not too distant future. And then looking at the horizon, where we're going with these kind of hybrid methods or IMSRD-based methods towards predictive ab initio theory with systematic uncertainties, and where we can guarantee convergence to the exact results. We're constantly expanding the capabilities, so spectra, radii, transitions are there. The next thing in the coming decade will be clustering and making the bridge to dynamics and reactions. And then my personal dream is that we can make this framework so scalable that you can essentially at some point use it in your day-to-day data analysis, maybe then with some increased uncertainties. And in the cases that are particularly interesting, then you tighten the accuracies and you go to some of the largest computers that are available to the community at this point. And with that, I want to thank all the collaborators or people who I've had relevant discussions with, I should say, and I want to thank you for your attention. I guess the funding agencies should get their thanks too.
Thank you, Heiko. Are there questions at this point? I just go ahead and unmute yourself in case you. Oh, Bai Shan Wu, if I'm saying that correctly.
Yeah. Can you hear me?
Yeah. Hi, Bai Shan.
Okay, hi. Thank you. Very nice talk. And I have two questions about the. You showed the magnesium B2 and the radio. I saw radio is underestimated, but B2 is very good. So you might understand the E2 operator also linked to R square. So this means E2 not so sensitive to R square. Another question. Oh yeah, this question. Yeah, first question.
No, you're absolutely right that this is an inconsistency in some sense, right? Since the radii are like 5% too small and the BE2s are right on top of experiment. As I said, I think that's an accident. So if you had an interaction, I mean, presumably if you go to a more consistent interaction and a more consistent transition operator, maybe with currents that has been built on with the same LECs as the interaction, then you will get a more consistent picture out of that. But kind of the main point, I think, in a way, is that the method seems to be able to handle these types of correlations here. So then if we have the better input, we will probably get, we probably will be able to resolve that discrepancy or that inconsistency.
Okay. Okay, I see. Okay, thank you. And another question is about emulator for immediate SRG. So I know they have a de-excited operator, difficult for construct emulator. So do you have any idea?
Yeah, I mean, the challenge is that in the IMSRD, compared to other methods, there's these nice techniques with eigenvector continuation out there, but they are all formulated in Hilbert space. And for the IMSRD, what you really want is an emulation in the space of theories or in the algebra of operators. So that's kind of a different problem. But as I don't want to say too much, but I think we have a way of doing that now, and we're working on a paper that will hopefully be out soon.
Okay. I'm looking at this paper. Okay, thank you.
So one more question from Zhangming Yao, if I say this correctly.
Yeah. So yeah, I would like to make comment to the question raised by some regarding to the BE2 and the charge radio. So yeah. Firstly, definitely we need more investigation. I mean, this is still not fully. I mean, this project is not fully complete. The important point that I want to say is that the charge radio is actually just for the ground states, but the BE2 value is calculated use the wave function of 0 plus state and 2 plus state. So it corresponds to the off diagram. So in some of the nuclear, it happens that the correct wave function in ground states are different from the data in the excited state, 2 plus states. So it may happen, even though it's not so frequently, but it may happen that they are not exactly corresponding to each other. So you see for some, for example, neutron number equal 18, you see the BE2 is smaller than the experiment data. And also for 22, so I mean the BE2 value. So yeah, that's my reply.
Okay, thank you.
All right.
Makes sense.
So thank you very much, Heiko, for the wonderful talk.
Thank you. I hope you can all hear me clearly. I've had some internet instabilities a few times, so I hope the quality is good. So yeah, first I'd like to of course thank the organizers for this opportunity to talk to you about nuclear physics opportunities with electromagnetic moments beyond the quadrupole. In fact, I will only really talk about one of these specifically. I will talk about the magnetic octupole moment. There's other things that could be talked about, of course. Electric hexadecupole moments, for example. There's some things that we could say about that. Anastasia is saying she does not see my slides. I hope.
I can see them.
Okay, good.
Interesting. I'll try to log in again. So it's a local problem rather than the general one. Okay, sorry.
Yeah, no worries. I hope it works out. So anyway, I will focus on just the magnetic octupole moment. You could also think about magnetic quadrupole moments, for example, beyond standard model physics along those lines. Again, that's not something I will talk about. I will stick to magnetic octupole moments. Now, what are they, or where do they come from? How can we figure out what they might be? So let's have a look at that and start from the hyperfine structure of atoms. It's been mentioned, I think, a few times by a few speakers, but I'll nevertheless go over that a little bit. So we know that if you look at the energy levels of an atom, we know that every fine structure level is split into sublevels, and this is because of the presence of the non-zero nuclear moments. And what we typically do, at least in the field of nuclear physics research, is we treat this hyperfine structure to the level of the magnetic dipole and the electric quadrupole moment. And you see here a long formula that sort of gives you the splitting as a function of these two moments. Basically, it's a bunch of spin angular momentum couplings multiplied by these nuclear moments. So you see here the dipole.
So did you move your slides? Because maybe I'm the only one that now I didn't see your slide moving. I still see the title slide.
I see.
And I still don't see them at all.
Okay, so there's a problem there. Let me do that differently. Let me just share maybe my screen. So if I share this, does that then show something better?
Still black for me.
Still black, interesting.
I don't know if others see it or not.
Okay, let's try something else.
Ah, see, it's also black for someone else.
Good. Well, good, not good, I don't know. Let's try like this. If I just share my whole screen, maybe that will help. How does this look?
Black. Sorry.
So we're not making progress. Interesting.
I see a tiny white square now. It's really weird. I've never seen this problem.
There was a quick flash of a slide just now, but
interesting. I even was kicked out of Zoom briefly, so I have to say this is the first time it goes this poorly via Zoom. Let's try again. How about now?
Yes, I see them.
Very good. I don't know what was going wrong then, but seems like we're back. Good.
And you are moving between them as well, so I think it's okay.
Excellent, excellent. I hope now it works for everyone and not just for Anastasia, because that would also not be possible.
Yes, that would solve my problem, but to create others, I guess.
Yeah,
Good.
that's good.
Thanks, good to hear. So hyperfine structure, right? The splitting of atomic levels into sublevels because of the presence of non-zero nuclear moments. And at least in my field, we always stop after the quadrupole. But that's of course only an approximation. In principle, this multipole expansion of the hyperfine interaction goes to arbitrary orders. And so the next term that would be allowed would be a magnetic octopole contribution. Of course, in addition to that, if you look at things with a high enough resolution or a high enough precision, you should also worry about second order hyperfine structure, sometimes also called hyperfine mixing. And there's also things like hyperfine anomaly effects, which at some level of precision you have to worry about. So then in the rest of the talk, then I will add this one term here. I won't write this spin term out in full. This F function there, it gets pretty long, and as you go to higher and higher orders, it gets only longer and longer. But the basic principle is the same. You somehow the shift of a level in the atomic structure is proportional to some constant times some spin factors, and this constant is then the product of the moment and some atomic structure matrix element. So something related to the actual fine structure level. So we've been using laser spectroscopy techniques, hyperfine structure measurement techniques for, well, basically almost as long as nuclear physics as a discipline is around, to measure magnetic dipole moments. And over these decades, this has proven to be an exceedingly powerful and useful probe to learn more about nuclear configurations, basically answering the question, what orbit would a valence proton or neutron find itself in, for example. We've also been able, especially in recent years, to not just study stable isotopes, we've measured magnetic dipole moments of very long chains of radioactive isotopes. You've seen it, for example, in Kieran's talk just today, how we can cover this whole nuclear chart pretty extensively. And so this allows us to investigate how nuclear structure changes as we approach shell closures, go into regions with deformation, etc. From this rich data set, we've been able to compare to nuclear theory as well, and this has proven a very powerful tool to guide theory, to benchmark it, and to point out where maybe things can be improved. Now, when you turn to magnetic octopole moments, it gets a little bit harder. If you look at the definition, in a way, the value of this moment should give you information not just on, it should give you information on how the magnetization distribution in a way deviates from spherical symmetry. That's one way of looking at it. So we no longer consider this magnetization as simply giving rise to a point-like dipole effect. No, you get sensitive to the distribution of magnetization as well. This is somehow schematically illustrated a little bit on the right. So the top configuration, these arrows somehow indicate current flow, let's say, in the nucleus. A configuration like the one shown above the lambda equals 1 gives rise to a non-zero dipole moment. But if you start adding this sort of twisted or torsion into the current flow, you will get non-zero octopole moments as well. This figure was made by Jacek, who will give a talk on Friday, and will perhaps also speak about this. I'm not sure. Now I say that's really all I can say about them, because in a way there's only been 20 measurements to date, and by 20 measurements I mean there's only been 20 elements or isotopes for which a magnetic octopole moment has been measured. And the scarcity of data makes it difficult to do in-depth discussions or comparisons to theory. I'll nevertheless give it my best shot in the next few slides. But yeah, so instead of showing the whole nuclear chart, as Kieran did, where every little square was an isotope for which a measurement has been performed, it's much more space efficient for octopole moments to just show the periodic table. So everything in green has had an octopole moment measured, whereas in orange, either the precision was not sufficient to allow a meaningful discussion of what the value means, or the octopole effect on the hyperfine structure has been determined, but was not turned into an actual value for the moment. So if I go back a couple slides, what I mean is this whole term here was somehow measured and found to be non-zero, but the step was not taken to evaluate the atomic structure side of things to actually gain access to the moment. You will see also this is, for example, for europium or gadolinium, which are not the most straightforward atoms to compute things for. So it's for good reason, I suppose. Now, what can we then say about what has been measured so far, about those 20 values? And again, I'll take a step back to first talk about the dipoles, because that's where we do have some intuition. And I'll stick to the level of theoretical interpretation that we can also use for the magnetic octopole moments. That is, let's have a look at what we call the single particle estimates. So this is the most simple model you could possibly write down. You basically say, okay, I have a nucleus with an odd number of nucleons in it. I will only consider the effect of that one last valence proton or neutron, and I will treat the entire rest of the nucleons as an inert core. And you can then easily work out, and Schmidt did this already early last century. You can work out what kind of dipole moments you expect then. You get these black lines here. If you take a slightly more effective view on things, you get these colored orange and blue lines. And you can see then the dots on this plot are the experimental data. And you can see actually this extreme single particle model does a pretty good job, as long as you're willing to use this effective G factor, as it's called, this quenched G factor. As long as you're willing to do that, you find a global reproduction of the measured values, which works pretty well. Another thing that Kieran also showed as well was these magnetic moments over a chain of indium isotopes. So here, whereas the dots here, I believe, on the top plot are mostly stable isotopes, here you can add different isotopes of the same element. And he mentioned this constancy of the magnetic moments of indium, which again sort of lends credibility to this single particle theory or model, if you will, showing that the number of neutrons in this core doesn't really matter. All that matters is this unpaired proton in this case. And it's been considered one of the textbook cases to demonstrate the validity, if you will, of the shell model, or the success of the shell model. And so because of that, as Kieran also mentioned, these indium isotopes are somehow considered to exhibit a very clear single particle-like structure, and were quoted as a textbook example of that. Now we can do the same. We can also make these Schmidt lines for magnetic octopole moments. This was not done by Schmidt. This was done by Schwarz, and so therefore we call them the Schwarz lines, and they're shown here on the right with the same color. So depending on the relative alignment of the orbital and the spin angular momentum, you get these two different lines. And I've shown you here, I think 17 out of the 20 data points that we have, and well, what you can see is that in a way, it also works reasonably well. You have these isotopes here with spin 3/2. For those, it actually works as well as you could hope for. 209 bismuth does it's also very well reproduced, but then there are some very clear deviations. Iodine 127, in fact, lies closer to the wrong line, if you will. It should really land close to the blue line. It doesn't, it lands close to the orange. Interestingly, cesium 133 does the exact same thing. Instead of landing on the orange line for the J equals L minus a half, in fact, it lands closer to L plus a half. And then indium, this textbook case, as I said, of single particle-like behavior, in fact, lands in between the two lines, and so does not exhibit this good agreement with the Schwarz lines. And so it's a bit of a question, at least from my side, why that is. There's not much theoretical literature on this. There were some papers in the early 50s. Who discussed this, basically raising the same point I just did. Why are the deviations so much larger for magnetic octopole moments? And somehow the conclusion has to be that there's a bigger sensitivity to configuration mixing, or configuration mixing, or collectivity, or deformation. That's sort of the best guess as to what's going on. But there hasn't really been any modern nuclear theory attempt at understanding this, other than one that I will discuss a little bit in the next slides. Before proceeding though, and over-interpreting perhaps, we should be cautious. One, there's not many measurements. Two, there's usually only one measurement for any given element or isotope. And three, all of them in some way rely on atomic calculations of the C over omega ratio. And some of these calculations were done sort of, well, I don't know, empirically effectively a long time ago. So we can wonder out loud whether or not they are accurate. We can also wonder if the measurements are reliable, since they've never really been repeated. I'm sure they're precise, but are they also accurate? Are there systematic effects which may have been missed? I don't know, and that's something that would be interesting to find out. So I'd say that a critical survey of the literature through the lens of current atomic theory and nuclear theory would be of interest, as well as an investigation also on the experimental side of things, with maybe some remeasurements of these values, some of which are from the early 50s. So they could definitely, it might be worth having another look at them. Now, with that caveat out of the way, let's take this value for indium at face value. Let's say, okay, let's assume that this is somehow accurate. I just find it interesting to put it alongside what Kieran talked about earlier, right? How by pushing our measurements towards n equals 82, we somehow maybe put some question marks next to this interpretation of this single particle character of all of these other indium isotopes. Perhaps the clue was there in the literature all along. Maybe this deviation for the octuple moment was already an indication that there was a bit more complexity in this wave function than we expected. But I have to say, this is really pure speculation on my side, and it would be very interesting to get the opinion of a nuclear theorist and actually see some calculations and see if this somehow tracks or works out in the end. I don't know what the answer is there. What I think I can say though with confidence is that there is complementarity or complementary value in exploring this next order magnetic observable. And I think we can learn a lot if you could do this a bit more systematically and for more elements and more isotopes. So then, as an experimentalist, let me comment on what I feel qualified to comment on. How can we move forwards? How can we try and contribute? And I'll give some general thoughts maybe a bit later. I'll start by showing what I've tried to do to contribute myself. I tried to measure the magnetic, or I succeeded as well, in measuring the magnetic octupole moments of scandium-45. Why scandium? Nuclear physicists in the audience will probably appreciate why. It's a single proton outside of a calcium core. So if there's any isotope for which you might hope that a variety of nuclear theories would be able to do a good job, it's probably scandium-45. Now, if you measure the hyperfine structures of the scandium-45 with the conventional laser technique, conventional laser spectroscopy method, like what we've heard about in this session and also last sessions, you will get spectra like what's shown here in C and D, and you will find you are nowhere near precise enough or accurate enough to extract a meaningful magnetic octupole moment. The line with basically the width of the peaks is somehow at the megahertz level, tens of megahertz level, which is limited by the lifetime of this excited state. So conventional laser spectroscopy is definitely not the way to do it. Instead, one way of approaching it is by doing a direct probing of the hyperfine separations by doing radio frequency or microwave excitations within the ground state or metastable state hyperfine manifold. And because these states have an infinite lifetime, essentially infinite lifetime, you can do this very carefully with a very long interaction time, and you can therefore reduce your line widths considerably. And so that's what I set out to do for stable scandium-45. And rather than going into the detail of how such a measurement is performed, let me just skip ahead to the conclusions. You see some of these spectra here. The thing you should note, I think, is the width of these lines, of these individual transitions. They're about 20 kilohertz wide. If I just go back to the previous slides, the conventional laser data is more like 50 to 100 megahertz or so. So this is about 3 orders of magnitude more precise. And this, of course, translates into a considerable improvement in the hyperfine constants as well. You can see here the final values that we obtained for the dipole, quadrupole, and octupole hyperfine shift. You can see also a corrected, uncorrected column here. Corrected means that the second order hyperfine interaction, which I mentioned at the start, that this was taken into account to the best of our ability. And you see that leads to slight shifts, which for dipole and quadrupole don't really change the story much, but for the octupole actually make a very significant difference. I can perhaps show that better using this plot here. So this shows the magnetic octopole moment which we extracted without these second order hyperfine corrections here for the 2 atomic states which we could do the measurement for, and then with the correction. And you can see that clearly improves the mutual agreement between the 2 measurements. And then doing the weighted average of those, you get the green data point here, which we could then start to compare to theoretical values. So the Schwartz limit, which I mentioned earlier, is this red line, and then a shell model calculation, and then the DFT calculations done by Jacek underneath that. Now, what I think is interesting to note is that these more advanced calculations tend to reduce the values of the octopole moments. That's a general prediction they already made actually in the 50s, that increasing the collectivity or increasing the complexity, sorry, of these wave functions will tend to reduce the values of the magnetic octopole moment. We see that here in effect on this plot. So that's the contribution I try to make myself. How can we go beyond this? So let me just go back again. You see here the error bar that I wound up with is still a bit big. So we'd have to do at least a factor 10 or so better to do a more refined comparison to theory. So that's one thing that I think I personally will work on. But more in general, if you sort of take a step back and look at what we could do as a collective, as a team, there's, I think, a lot of value in exploring these conventional laser double resonance experiments like what I showed you there on the previous slide. And in fact, there's lots and lots of room to stick to the stable ion beam laboratory and actually study many, many more of these stable elements. The ones that have been measured have all been measured with some form of atomic beam magnetic resonance, except barium. I'll come back to that. And I think technologically a lot has changed since the 50s, 60s, 70s when most of these measurements were done. So I'm convinced we can make significant headway in exploring more and more elements, even with stable isotopes. But also, as I think Kieran has shown, there's of course tremendous value in exploring radioactive isotopes as well. Going further from stability, looking for structural changes, seeing what deformation does, seeing what happens when we cross shell closures, etc. That's something that I think would be very, very valuable. And so pushing to do collinear laser double resonance measurements, for example, I think is definitely possible with our current technology and current instrumentation, and is something that I think we should push for and try to do. There's another step in precision that we could consider. So far, all of the measurements except the one that's presently being projected were done using thermal beams, basically in using this atomic beam magnetic resonance methods. But there has been, in the last decade or so, one measurement where instead of working with a thermal beam, an ultra cold ion inside of an ion trap was studied. And as you can imagine, putting ions inside of an ion trap means that you can extend your measurement time, your interaction time, even more, and it really allows you to push the precision down considerably. You can see here an example. So I showed you spectra that I obtained about 20 kilohertz line with. You can see here this is 50 hertz. So that's another 3 orders of magnitude. And then you can see what is by far the most precise measurement of a magnetic octopole moment to date underneath with sort of the sub-percent precision. So that's another angle that I think as a community we should not be afraid to explore, both with stable and eventually radioactive isotopes. Now, people who know the atomic structure side of things a bit will of course comment, yes, barium, everything is easy with barium. It's a very nice and simple electronic structure, which is, I think, also why it's the case to start with. But I just want to show here in another example, this was a measurement done on the europium, that it is in fact possible to do these kinds of precise measurements also for systems with a much more complicated atomic structure and a much more complicated nuclear structure potentially as well. So another thing, perhaps because I was very ambitious when I named my talk, and I said I was going to talk about moments beyond the quadrupole. There's another moment beyond the quadrupole. There's the electric hexadecapole moment, which has also been, they tried to assess it in this specific measurement here in europium. And you can see that there is some indication of a non-zero contribution of this moment within the precision of the measurements, but not to the point where they made any statements with any confidence on the value of this moment. So let me then sort of take that and wrap it up into a conclusion. I think it's safe to say that these higher order nuclear moments have only scarcely been explored, especially when you compare it to what's been done for dipole and quadrupole. I believe there's significant potential to learn more about nuclear structures, to provide more new information on the properties of the nucleus, especially to learn more about the magnetization of the nucleus. I think there's a lot of experimental opportunities, both in the stable ion beam labs as well as the radioactive ion beam laboratories. I think nuclear theory is ready for the challenge, but I put that in a question mark. I will leave it to the audience to comment. I hope as well that atomic theory is also willing and able to take up this challenge as well. It's not only required to extract the moment from the measurements in an accurate way, but I think also going forward in finding out which atomic state is the most sensitive to the underlying nuclear moment. I think having a dialogue there with atomic theory will be valuable, if not required. As a closing slide, let me just show that it seems to be, to me at least, that there is some interest, at least already in literature, with few papers from atomic theory point of view, starting to explore what is possible, what sensitivity would be for different atomic states, and I hope that only picks up as experimentalists try harder to measure them as well. And so with that, that's all I had prepared, and I'd like to thank you for your attention.
Thank you very much. Are there questions at this point? Okay, we have, I'm sorry, I see a hand is raised, but I don't know who raised that. Oh,
me maybe?
Yeah, yes, go ahead, please.
Yeah, hi Ruben, thank you for the nice talk. I think if you want to attract atomic theorists, you should not be talking about europium too much. That's
for sure.
Could you go back, please, to the slide with your results and the DFT model and the shell model?
Yeah, sure. Let me just go there. There you go.
Yeah. So I find it really, I don't know, really disturbing that something that you call corrections actually change the order and the size and the sign, right?
Yeah.
So in a sense, it's not really corrections anymore, right? It's
yeah, sure. So this is, in a way, is a general feature. So the order of magnitude of the octopole shift is comparable in many cases to the size of the second order hyperfine interaction. So this called it disturbing, which is a very uncomfortable adjective, but I agree there's definitely
uncomfortable. I think
yeah, uncomfortable, exactly.
Yeah,
I agree. So I think here, so one thing should be pointed out: if you do the measurements for the spin orbit partners, you sort of they shift oppositely for the two states because of this hyperfine interaction. So one thing is here, if the experiment is performed more precisely, I have a feeling this will look a lot less potentially disturbing. The error bars there are there for a reason, right? I'm sure the sign changes, but in errors it doesn't. So that's one comment I would definitely want to make. So with more precise measurements, I think this will become less, perhaps less disturbing. I would also want to add, this was also, for example, done for these values here in barium, because of the hyperfine interaction of the D3 and D5 halves. And there's also a very significant shift, but in this case, actually, again, required to bring them into mutual agreement as well.
Okay. And if we maybe I have something else on the same plot as before, because I see the models have some width, right? The shell model has some width and DFT is more narrow.
Yeah.
Does that represent the uncertainty or?
Yeah, in a way, yes. So again, here Jacek would be better placed to comment, but it's sort of calculations were done for a range of different parameters, and sort of this covers the band of the results coming out of the calculations. Is this too optimistic, too pessimistic, that I don't know so much, but that's in a way the range of values obtained within the calculations.
So it's within that model. It's not uncertainty with respect to the true picture in a sense, right? That,
yeah, exactly. Yeah, exactly.
Seems okay though for the uncertainty that the experimental measurements have, right? I mean,
well, but that's the point. If they narrow the experimental uncertainty, then and let's say it goes away from the DFT uncertainty, then what?
Yeah, exactly. So there's definitely a lot more work is needed here, right? This is, to my knowledge, the first time anyone has used a modern nuclear, like something more advanced than just a single particle estimate to calculate these things. So this requires really a more systematic investigation on, what's the impact of choosing different functionals, choosing different parameters, et cetera, that needs to be done in much more detail, also for the shell model. So there's a lot of work ahead on that front, definitely.
Okay, cool. Thank you very much.
Thank you for your questions.